Anchimeric assistance or neighboring group participation. So what is Anchimeric assistance or neighboring group participation? So this is very important to understand this. I have highlighted these a few examples in this slide. Let's see the very first is the structure number one and structure number two. If we compare their structural change, it has a good living group, which is a chlorine attached to a sp2, sp3 hybridized carbon. The same in structure number one, same chlorine is attached to the sp3 hybridized carbon. But only difference is structure number one at two position contains carbon, whereas in this structure number two, the at number two position it is not carbon, this is replaced by oxygen. This is the only difference between these two, structure number one and structure number two. But when we carry out the substitution reaction, so because if you remember, this is if you look at the CH2, this is a primary carbon. Very similar is here. This is also a primary carbon, although it is not attached with one oxygen carbon, but this is just like it is attached with the primary carbon. Second, this bond of carbon with chlorine is more polarized. Why more polarized? Because this oxygen is electron withdrawing, it is electron withdrawing electronic density from this carbon more than this. In this case, this carbon is electron donating. So this carbon has a minus I effect, and this oxygen has a it has a plus I effect. It is withdrawing electronic density. You can see this oxygen is more electronegative, and this carbon is, and these two carbon are same electronegative. So this carbon is electron donating. So when it is electron donating, it is plus I. This oxygen, which is opposite, it is withdrawing electronic density rather donating. So it is creating more positive charge, polarizing this carbon chlorine bond more. This is one obvious reason that it should have a higher reaction rate as compared with this one. Look at here, I have provided the data. There's a dx by dt, mean the rate of reaction of 1 and 2 is 1 ratio 10 to raise power 6, 10 to raise power 6 mean million times. If you compare this reaction rate, this is a huge difference that the substitution taking place at this carbon in structure number 1 versus the substitution taking place at this sp3 hybridized carbon in structure number 2. This is having a huge difference in reaction rate. If the reaction rate we take this as a standard, then the reaction rate of structure number 2 is 1 million times faster than first. So it cannot be only just to the electronic difference. This is plus I group and this is a minus I group. It cannot be this very huge difference cannot be due to this. There is something else operating here in this due course you shall see. This is called enchimeric assistance. In fact, when this group is leaving, this oxygen is present here, it donates electron pair here. So rather it follows SN2 mechanism, it follows the SN1 mechanism. So you have already come across the factors affecting substitution reactions in which you have come across the structure of substrate. This is due to this. So anyhow, I shall conclude this in next slide with the detailed mechanism, but just focus on here. There is a huge difference in the reaction rate of substitution. This carbon is sp3 hybridized. This is also sp3 hybridized. This carbon is primary carbon. This is also primary carbon. So both should undergo SN2. This reaction, no doubt, undergo SN2 mechanism, Walden inversion, but this reaction doesn't proceed via SN2 mechanism. In fact, it proceeds via SN1 mechanism. We shall see in next slide. Now focus on structure number 3 and structure number 4. What is here? Look at this chlorine. Same chlorine is here. It is attached with the carbon, but this carbon is not a primary carbon. This is a secondary carbon. You see, this is methyl, this is alkyl. So this carbon is a secondary carbon, not a primary carbon. Very similar if you focus on the structure number 4, it is also having a carbon, same chlorine, same methyl, but just difference. Here it is not an alkyl group, it is a benzene ring system present here. Now, this can proceed via SN1 or SN2. We are not concerned either it is proceeding via SN1 or SN2 because it depends upon the other factor, the polarity of the solvent. It also affects on the reaction conditions. There are so many other factors you have already come across. We are not focusing that at the moment. Either it follow SN1 or SN2, both are substitution. We are not concerned to that. We are just concerned with the reaction rate. This structure, if this is alkyl group, this is methyl, this carbon, so it shall not be favored by SN1. Why? Because the secondary carbocation shall not be stabilized much. But in this case, if this chlorine leaves first, it shall generate a positive charge here. So this positive charge you have already seen this. This is commonly called as benzylic cation. This benzylic cation shall be resonance stabilized. So this cation is more stable as compared to secondary carbocation. This is resonance stabilized. This is hyperconjugation stabilization. So as a result, what shall happen? This shall follow more SN1 mechanism rather SN2. If we look at the reaction rates, the reaction rate of 3 versus 4 is 10 to raise power 5, mean 100,000 times faster than 3. Again, this is showing this substrate is extraordinarily more reactive. All right. So here the electronegativity, electronic factors are same. This R is sp3 hybridized carbon, this R is sp2 hybridized. There is a very minute difference in electronegativity of sp2 hybridized carbon over sp3. sp2 is slightly more electronegative than sp3 hybridized carbon. So this carbon is slightly more electron negative. So it is making this carbon slightly more polarized. So it cannot afford that high electron difference in mechanism. This reaction rate cannot be that much high due to this minute difference in carbon. So it means something else is being operative here. That is in fact the neighboring group participation that we commonly call anchimeric resistance. So I shall explain this with mechanism in next slide. Now just focus on the structure number 5 and structure number 6. What this group is, if you remember, you have seen this is tosyl group and this AC stands for acetyl. This I have highlighted here. This is acetyl group in fact. But this carbon and this carbon both are sp3 hybridized. Here both of them are sp3 hybridized. Same substituent is attached here. Same substituent is attached here. In structure number 5, this acetate group is same position above the plane in this cyclohexyl group, and this tosyl is only changed. In structure number 5, this group is above the plane, and here this is behind the plane. This is the only difference. In fact, these two are diastereomers. You can see this carbon is uh, stereogenic center. This is also stereogenic center, having two asymmetric centers present, but one have same configuration, other have opposite configuration. This is a characteristic of a diastereomer. So structure number 5 and 6, they are diastereomers in fact. And if you remember, tosyl group is a better leaving group if we are comparing with acetates. Because if tosyl group leaves, it shall form 3 resonance forms. If acetate group leaves, it shall form 2 resonance form of the leaving group. So tosyl group is a better living group than acetyl group. So it means this group is going to. So both of these are having opposite configuration. Tosyl group in structure number 5 and structure number 6. Now if we compare here, there is no electronic factors. Just like there was a very minute electronic factor here, this carbon is sp2 hybridized, slightly more electronegative than this carbon, which is sp3 hybridized. This is a minute difference, but here there is a huge difference. This carbon and oxygen have definitely different inductive effects. So this is a minus I group, this is a plus I group. There is a much difference here, but this difference is not highlighted with the reaction rate variation. So this is which is very high, 1 million times. This is 100,000 times faster. So which doesn't indicate that it is due to this minute difference in electronic factors. But here there are no zero electronic factors. Same carbon attached with same substituent, same oxygen, oxygen is attached with same carbon. Just the difference is in their configuration. So there is no electronic factor or there is no mesomeric factor involved in this example. So it has been 100% neutralized. But look at the reaction rate. The structure number 5 is less reactive, but structure number 6 is more reactive. And the more reactive one is 670 times faster than the structure number 5. I have highlighted the structure of these two isomers, structure number 5 existing in chair conformation. So both of these two groups are 1, 2. At 1, 2 carbon they are present. Both are above the plane. So definitely one should go to equatorial, other shall go at the axial position. Tosyl group, because it is sterically more crowded, that's why it shall prefer to exist in equatorial conformation, and acetyl group, which is sterically less crowded, shall go to axial position. Now look at the other structure in which these two groups are opposite. Acetate have same position, but tosyl group has opposite. So that's why rather above the plane, it shall go behind the plane. And both groups are opposite to each other. They are in fact at this position, which is a tosyl group, axially downward, and acetate is axially upward. So this is the difference, geometrical stereogenic difference between structure number 5 and 6. This is a chair conformation. This is another chair conformation, but both of these two are opposite isomers. Now let's see the mechanism in next slide. The very first I have presented the case. Just look at there. Structure number 1, I am not presenting that. The second one, which are showing mechanism faster. Why the reaction rate, if you look at in previous example, this is undergoing simple SN2 mechanism because this is a primary carbon. But what about this? This is not following SN2 mechanism. In fact, it is following a different mechanism. First, what happens is Cl leaves. Why Cl is leaving? Because it is going to generate a positive charge, this one here, which is a primary carbon. This primary carbon, we already know this is not a very stabilized system, but do not forget the role of this next atom present here. Here we have an oxygen. Oxygen have two non-bonding electron pair. So it shall donate one non-bonding electron pair to stabilize positive charge on this carbon. We shall get this 2b resonance form. This resonance form have a positive charge on oxygen, but the positive charge here is stabilized. But in previous example, if you look at structure number 1, there is no such provision. If this Cl leaves first mean following SN1 mechanism, we shall have a positive charge on this carbon which shall not be resonance stabilized. Primary carbocations are not stable. So that's why this is not undergoing to follow a SN1 mechanism. It shall prefer to undergo a SN2 mechanism in fact. So It is following SN2 mechanism, but the structure number 2 is just a little change. We have replaced one carbon with oxygen. It is following a SN1 mechanism. Now you have seen this here. So the Cl leaves first in the first step, generating a carbocation, and in next step, this carbocation reacts. It is in fact stabilized by resonance, and then in next, what shall happen? Nucleophile shall approach this carbon, and this electron pair shall be transferred to this oxygen, in fact. So we shall get, in fact, here a nucleophile approaching the same carbon where substitution is taking place, but it shall result in the formation of an inversion in configuration and retention both, which we commonly call racemization. So this is following a SN1 mechanism rather SN2 mechanism. This is called neighboring group participation or Anchimeric assistance. What it stands for? It stands for that whenever a group closer to a living group is present, it make a big difference towards reaction rate. So neighboring group participation mean a functional group present in the neighbor of a living group. So this is a living group, a group which is present in neighbor. So this CH2 is attached with a functional group. So if it is a group which is a heteroatom present here, maybe nitrogen here, maybe sulfur, maybe anything else, which have at least one non-bonding electron pair present. So then it shall make a big difference towards the reactivity in reaction rate shall be very different. So this is a logical reason. Normally, sp2 hybridized carbon, which is sp3 hybridized carbon, which is primary carbon, always undergo SN2 mechanism, but it doesn't undergo SN2. It follows the SN1 mechanism because carbocation is not only primary. This oxygen is stabilizing the positive charge. Because cation is stabilized by resonance, that's why it shall prefer SN1 rather SN2. So mechanism is changed with neighboring group participation and the stereochemical outcome we obtain is entirely different. So we are getting a racemization at this point. Now look at the structure number 4 rather 3 does a difference. Here there is a benzene ring system present. In structure number 3 you have seen there is alkyl group present. So this group may follow because it is a prime secondary carbon here right now. Functional group is attached to a secondary carbon. If it leaves, it shall generate a carbocation here. All right. And if it undergo SN, it may undergo SN2 because both are competing. SN2, SN1, both are competing for a secondary carbon. But in this case, structure number 3, you have come across. So in structure number 3, it shall definitely follow a SN2 SN1 mixture, right? But if we look at the structure number 4, this one, in this case, it shall prefer SN1 mechanism again. Why? Because if this Cl leaves, no SN2, it shall result this positive charge, which is a secondary carbocation. But not only secondary carbocation, this secondary carbocation is resonance stabilized by this phenyl. I have drawn one resonance form only. So you can draw the other resonance form like this. It is presenting like this, and then it is going back here, the positive charge. It shall have a 5 resonance forms. This group having just 2 resonance forms, you have seen this is a huge difference in their reactivity, in their stabilization of carbocation. It has 5 resonance forms, so it has more resonance forms. So this positive charge is more stabilized. So it shall not follow SN1 mechanism, it shall follow SN2. Structure number 3 shall follow SN1 versus SN2 both, but it depends upon the reaction condition. We are using polar solvent and we are going for kinetically controlled condition, then SN2 shall be favored in non-polar solvents. But if it is polar solvent and thermodynamic condition, so in that case SN1 shall be dominating over SN2. So you have this already come across in structure number 3. But structure number 4 shall 100% follow SN1 mechanism, because if it leaves Cl, it shall generate a secondary carbocation which is resonance stabilized. So it shall follow SN1 mechanism. So structure number 3 and 4 are following different mechanism as well, and reaction rate is very high because it generate easily this one, which undergo uh, reaction with the nucleophile. But in structure number 3, this carbon is typically more crowded, so that's why nucleophile is not approaching very easily to this to undergo FN2 mechanism. So this is the reason why this is 100,000 times more faster than this one. Now look at the structure number 5 versus 6. In structure number 5, if you look at critically, whenever a group leaves, so this is, you shall see elimination reaction in our next topic for next week, uh, is in fact also this one, uh, elimination reactions. So, but just we are focusing at the moment on the aliphatic substitution reaction. In the last type of the substitution reaction, we shall focus on in uh, next lecture about the uh, aliphatic electrophilic substitution, not nucleophilic. This is the fourth type of the substitution reaction we shall focus in next lecture. But next week we shall start with elimination reaction. Elimination reaction has a very important aspect, that the two living groups, one living with electron pair, other shall be living without electron pair. And whenever they leave, there must be, the both living groups will be at 180 degree to each other. If this group is leaving from here, it cannot leave. So if it is not going to leave, because this is the most stable, it should have a hydrogen present at axial. This group should be at axial position, like in structure number 6. If this group is leaving from here, a hydrogen which is present here at axial position, so this group can leave without electron pair, and this can leave with electron pair. So it is 180 degree. This group is axially downward, it should be axially upward, 180. So this hydrogen can leave. Whereas on this carbon, there is a acetyl group, there is no hydrogen here, so this cannot leave. So only this hydrogen can leave, so it can generate a double bond at this position. Now you can see this in mechanism here. Structure number 6 is basically undergoing the loss of this group. If let's see, it will leave like this. So just focus, it shall result in the formation of a carbocation, which is this. This is not stabilized by resonance, because if oxygen is present here or there, it could be stabilized. It is not present there. This oxygen cannot stabilize this. But look at this non-bonding electron pair present on this oxygen. If I present this in another form, if this oxygen is making a carbonyl bond, this carbonyl is very straightforward like this, very straight to this. Now you can see this is a five-membered ring. A five-membered ring is formed. This oxygen present here is donating electronic density to this carbon and generating another form, this one. This is in fact, a classical carbocation, but a non-bonding electron pair from far away. So by bonding, this is far away from it, but it is participating in this case. So it is stabilizing this positive charge here. These are the two resonance forms in web 6A and 6B. But you can see this positive charge is stabilized here. So if this structure number 6, this group leaves, then the positive charge is stabilized by this acetyl group. All right. So this acetoxy group is stabilizing this positive charge. But in previous example, if you look at here, due to electronic condition, this group at this position cannot leave. All right. if I draw the other chair of this, if this chair flips, then axial subsequent go to equatorial and equatorial goes to axial. This shall go at this position. All right, very similar to this. But this group shall not be present here. It shall go to equatorial position. If this group is here and this group is equatorial, if this group leaves, generate a positive charge here. Now this group is not present here. It is present at